Right now, most of what we can do for the microbiome and health is for blood glucose control, and the reason why is we have continuous monitoring for blood glucose, so when you eat something you see the change very rapidly. What we need is sensors for other molecules in the blood besides glucose, including molecules that contribute to inflammation, so that we can much more rapidly find the relationship between the microbiome and chronic conditions like obesity or aging, where you might need months or years to find the results rather than minutes like with glucose. The other thing we need is more studies in animals with shorter lifespans, because if I want to find the relationship between the microbiome and diet and the human lifespan in people who live to age 100, if I started today, I would not have the results for 100 years, and that is a long time to wait. Whereas if I do it in a mouse with a lifespan of 3 years, or in a fish with a lifespan of 3 months, then I can see much better the impact of the microbiome on aging, although not everything we do in an animal will translate to a human. It is very possible to choose a diet that is both good for us and good for the planet. Many of the things that are worse for us, such as red meat and processed red meat, especially bacon, ham and so on, those are terrible from an environmental standpoint as well as from a health standpoint. And many of the foods that are most healthy for us, such as whole grains, such as vegetables, such as fruit, those are also good for the planet. There are a few cases where we must choose. So sugar-sweetened beverages, sodas and so on, those are not terrible for the planet because they are cheap to produce, but they are very bad for us. But in general, what is good for us is also good for our environment. Different people are totally different in their microbiome, so even your family members, you may be mostly different in terms of your microbiome from, let alone a person you meet on the street or a person from another country. For this reason, it is very important not to just study the microbiome in the United States, but to study it around the world. And the citizen science project that I run, the American Gut Project, we are now partnering with many different countries under the MicroZeta initiative to launch projects in each country, sometimes citizen science, sometimes with government support, sometimes with support from companies, so that we can truly understand these microbiome differences around the world, how they contribute to different patterns of infectious and chronic diseases in different countries, which the microbiome can make you susceptible to or can help you resist, and also what is common to all of humanity in terms of our microbial symbionts that we have evolved together with for millions of years. One very important aspect is to study the microbiomes of indigenous peoples, and especially indigenous peoples living traditional lifestyles, because as soon as you start to participate in industrialized society, take antibiotics, eat ultra-processed foods, many of your natural microbes disappear, and we must conserve these microbes that are disappearing before it is too late to use them to benefit the health of all of humanity. We have worked with researchers and with indigenous peoples in Venezuela and in Peru and in Brazil to look at the indigenous microbiomes and compare people who have less or more market participation in terms of living very far out in the rainforest versus living in cities in modern dwellings and so on. We have not done anything as far south as this. It would be fascinating to look at the microbiomes of indigenous peoples who are left in Chile and Argentina and to see whether the patterns are similar to what we see elsewhere. Especially with the obesity crisis in Chile, there is a very strong motivation to understand what can be learned from traditional peoples who did not have this problem, and even from a century ago when this problem did not exist, to start to understand what are the differences between now and then. And we know from studies of both humans and animals that the microbiome has a large role to play in obesity. We search for connection between microbiome and disease in several ways. The first is with population studies and epidemiology, where we sequence the DNA from the microbiome from many people, and we ask, using artificial intelligence and machine learning, we ask what kinds of microbes correlate with being heavy or thin, sick or healthy. We also we then do mechanistic studies in animals and in other laboratory systems. So what we do is we take microbes from different people, say who are fat or thin, or who have cancer or are cancer-free, and so on, and we add those microbes into mice to see if we can change whether or not the mice have disease. And we also do it in a test tube to see what molecules those microbes can produce. And we can do that when we feed the microbes different diets, like different people would eat, to understand the relationship between the diet and the microbiome and health. And then ultimately we can come back and test in humans through procedures like fecal transplant, taking the microbes from someone who is healthy and giving them to someone who is sick, which is more than 90% effective for Clostridium difficile, where antibiotics only have 30% effectiveness. We can try in humans supplying microbes back or destroying the microbes that we think are bad from these studies and proving that it works for human health. Now, all of this is a long process, and in general, the timeline between finding something from epidemiology or finding something in the lab and using it to improve human health is from 10 to 30 years, especially if you must discover a new pathway and a new drug and understand the mechanism of that drug and do clinical trials. That will take 30 years. But of tremendous interest is what existing medicine alters the microbiome and what existing foods alter the microbiome, because if we find something out there, we can translate it into action to help human health very rapidly. And that is what we focus on in my lab.